All right, hello guys, we're back again with another video. This is for section 10.4, and this is on the Laplace transform of a derivative. We've been talking about Laplace transforms within the context of using them to solve differential equations. The idea is that what I'm going to do is I'm going to take a differential equation. Instead of just solving it, what I'm going to do is I'm going to translate it using Laplace transforms. Okay, so I get whatever the Laplace transform of that is. Okay, I'll solve that. That, of course, gives me the Laplace transform of my answer. And then just untranslate that to get my solution. And that's, again, it seems like more steps to go through this, but again, it's easier. And the reason is this step here, solving this while it's inside Laplace transforms, is easier. But in order to do that, we've talked about it in previous lectures. We've talked about the ability to translate various functions. We talked about the ability to untranslate various structures we may end up with on the back end of these things. But what we haven't talked about is how do I translate, let's say, y prime, right? Laplace transform of a function, but I don't know how to translate the Laplace transform of maybe the derivative function. So we'll talk about that, and then we'll talk about how we're going to use this to actually solve some initial value problems. So as normal, prerequisite skills. Here we just have a couple. Some basic integration techniques. That's really just for the proofs. Okay, that's really just for the proofs. Laplace formulas. We'll need that when we work the initial value problems. And as usual, we'll need partial fraction decomposition. God, I love partial fraction decomposition. Seriously, that might be one of my favorite things ever. Okay. Okay. So let's go ahead and talk about. Suppose I have a function, and I would like the Laplace transform of f prime of x. So what is that? Well, you know what? So I don't have one of my nice translations for it yet. Let's go ahead and put it into the definition of the Laplace transform, right? So by definition, this is the integral from 0 to infinity of e to the negative st. You know what? I wrote f of x here. That's supposed to be f of t. It doesn't really matter, but you know. Times f prime of t dt. Now I realize we won't be able to get an explicit solution here because, of course, I don't know what the hell f of t is. But maybe I can rearrange this to where this will be a little bit nicer. Okay. So what I'm going to do is I'm going to do some integration by parts. Okay. I'm going to do some integration by parts. Let me go ahead. I'm actually going to I'll write the parts out here. See, what I'd like to do is this seems very, very close to the original definition for just the Laplace transform of f. In fact, the only difference is, of course, that prime is there. But what if I do integration by parts, and what if I call u e to the negative st and dv f prime of t dt? The remaining parts here, v would just be f of t. Of course, this is, again, the integral. And du would, of course, be... Now, remember, I'm taking the derivative with respect to t, so s is technically a constant. So this would be negative s e to the negative st dt. And let's see what I get when I put those things in there. Now, we have to be very, very careful when we're splitting this. This is a definite integral. I do have some bounds, and, of course, those bounds are improper. So let me change this to the limit as n approaches infinity of, okay, here we go. So it's u times v minus the integral of v to u. So that's e to the negative st times f of t evaluated from 0 to n minus v du, minus the integral of v du. So that's minus the integral of, from 0 to n, negative s e to the negative st times f of t dt. All right, let's see what we have here. This, I get the limit as n approaches infinity of, so again, plug in n, plug in 0. I plug in n first, I get e to the negative s times n times f of n minus e to the negative s times 0 times f of 0. I'm going to pull out the negative s here. We'll make that a plus s times the integral from 0 to n times e to negative s t times f of t dt. Okay. Let's see what we have here. So as n travels towards infinity, again, n is going to end up being positive. I realize s needs to be positive for this to actually converge, right? Otherwise, this will be. Otherwise, this won't converge. It'll expand infinitely. It'll explode. But we'll assume s is greater than 0. It's not a huge problem. We've been making assumptions about the value of s for all of these Laplace transforms. Anyway, so we'll assume that. Here we go. So this term goes to 0 then. This term, well, that's 1. So that's f of 0 times 1. Now, I don't know what f of 0 is, but that's okay, right? So that's negative f of 0. Okay. And if I'm being perfectly honest, again, I don't know what that is. So I'm going to call that the integral from 0 to infinity, again, because limit is n approaching infinity, of e to the negative st times f of t dt. But this is actually really, really nice. This is actually really nice. Because look at this form. Isn't this the formula for the Laplace transform of f? And so what I have, if I rearrange this, I have s times the Laplace transform of f of t minus f of 0. Yeah, that's the Laplace transform of f prime. And so what have I done? What I've done is that we now have a way to write the Laplace transform of y prime in terms of the Laplace transform of y. This is fantastic, right? It means if I take the Laplace transform of a differential equation and I have to take the Laplace transform of y prime and y, I'm not going to come out with two different Laplace transform terms. Since I won't know what they are, I'm going to have one type of Laplace transform term, just the Laplace transform of y. Now, it gets even better because the way this is constructed, this particular formula here is iterative. I can apply it over and over again. Okay, so I'm going to erase this, but I'm going to put this back on the board in a bit. So in general, I have the following formula. So I have the Laplace transform of f prime is s times the Laplace transform of f minus f of 0. Okay, so what if I wanted the Laplace transform of, well, let's say the nth derivative of f. So not the first derivative, but let's say second, third, fourth derivative. Well, applying this same formula, notice that this function is the derivative of this one. So I can write this the same way. I can write this as s times the Laplace transform of the n minus first derivative of f minus the value of that n minus first derivative at 0. Right? I can extrapolate this formula to any given derivative, and then I can take the formula and apply it again, because this can be expanded using the same formula, right? And the next one can be expanded, the next one can be expanded over and over and over again, right? So now, admittedly, that's going to end up getting long, right? It gets longer every time. But let me go ahead and spoil this for you. Really, we're only going to need the first and second ones. So let me derive out the second derivative just so that we have it. We can write it down. So if I want the Laplace transform of f double prime, that's s times the Laplace transform of f prime minus f prime of 0. Again, now replacing this with my formula here, I get s times, okay, so this gets replaced with s times the Laplace transform of f minus f of 0 minus f prime of 0. And distributing, we have this formula here, which we're going to use for the Laplace transform of f double prime. I have s squared times the Laplace transform of f minus s times f of 0 minus f prime of 0. So this polynomial type term here will just get longer as we apply it to larger and larger derivatives of f. Okay? Yeah, this is great. So this allows me to solve some of these initial value problems. Now, it also throws a bit of a monkey wrench into what we're doing, because what you'll notice is that in order for me to solve one of these, or in order for me to create one of these Laplace transforms, I need the initial values, right? I need f of 0, f prime of 0. So I will require these things whenever I'm working with Laplace transforms, using them to solve differential equations. But that's not really that bad, okay? Most of the times we're using these things in industry, we'll be able to ascertain the initial conditions from whatever we're starting from fairly easily, right? I mean, I know how much, I know how much is going through my system when the system's turned off, right? Yeah, at time 0. So, okay, let's actually work a problem and see how this works in a practical sense. Okay, so let me pull out one here. All right, this looks fun. Okay, so I've got y double prime minus y is equal to 12 e to the 2t. And I've got a couple initial conditions here. Y of 0 is 1. And y prime of 0 is also 1. Okay. All right, let's see what we've got. Okay. So we'll start by, again, translating this, right? By using my Laplace transforms to take this and rewrite it. And something very, very nice happens whenever I do that, okay? So let me go ahead and take the Laplace transform of everything in this equation here. So I've got the Laplace transform of y double prime minus the Laplace transform of y. Remember that the Laplace transform, it's a linear transformation, right? So it's scalar invariant, it's additive. The linearity here allows me to do this distribution, okay? Is equal to the Laplace transform, don't forget to do this side, of 12e to the 2t. Okay, so let's replace these things with what we know them to be, okay? Laplace transform of y double prime, that is s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. Okay, so this is all of this. This is the Laplace transform of y double prime. Okay, minus Laplace transform of y. You know, very commonly I see students end up getting lost in these things once they're translating a lot of things, and they don't make sure that every single thing in their original equation is represented here, right? They'll get lost in the middle, so try not to do that, okay? And that equals the Laplace transform of 12e to the 2t. Now I know that 12 is irrelevant, this is scalar invariant, but the Laplace transform of e to the 2t is 1 over s minus a, or s minus 2 in this case, so I get 12 over s minus 2. Okay, now, you'll notice this entire equation now is linear in the Laplace transform of y. I can solve for the Laplace transform of y, and I'm going to do that right now. I'll start. Let me move everything that doesn't have Laplace transform y over to the other side. Now you'll notice I do have a y of 0 and a y prime of 0 here. Both of these things are 1. Those are my initial conditions, right? So I do know that that equals 1. And I do know that this also equals 1. Okay. So let me go ahead and rewrite these. I'll keep the s squared Laplace transform y and Laplace transform y. So I've got s squared times Laplace transform y minus Laplace transform y. Okay. On the right-hand side, I'm going to have 12 over s minus 2. And then, of course, I'll move these two terms. This is negative s times 1, or just negative s. This is negative 1. So that'll be a positive s and a positive 1. Okay. Now I'm going to do a little bit of simplification on the right-hand side. On the left-hand side, I'm going to factor out Laplace transform of y. So on the left-hand side, I have s squared minus 1 times the Laplace transform of y. And on the right-hand side, I'm going to, I'm actually going to add these two things together, right? So this is s plus 1, technically, we could call this s plus 1 times s minus 2 over s minus 2, right? Okay, that gives me my common denominators. I can actually add those things together. All right, so that gives me s squared minus s plus 10. Okay, so I get s squared minus s minus 2, but I got to add the 12 into the minus 2. That gives me positive 10, and this is all over s minus 2. Clearly, I can solve for Laplace transform of y by just dividing over these factors here, and I'm going to write Laplace transform of y is equal to, I now have s squared minus s plus 10. Now I'm going to factor, this is s squared minus 1, and instead of writing s squared minus 1, I'm going to write s plus 1, s minus 1, of course. Why? Well, so what do I know now? Well, I'm basically done. I know that the inverse Laplace transform of the Laplace transform of y is just y. Yeah? So I can solve for y by just taking the inverse Laplace transform of both sides. I basically have my solution, right? My solution is y is equal to the inverse Laplace transform of s squared minus s plus 10 over s minus 2 s plus 1 s minus 1. Okay? Now, of course, I'm not finished because I can actually invert this, right? So we talked about the 3 steps, right? First, I was going to translate it. That's what happened here. Then, while it was translated, I was going to solve it, right? That's what happened here. I've now solved for y just by translating this, and the solving was just algebra. It was just solving a linear equation, basically. Okay? Well, maybe some little complications here, but still. And now all I have to do to get the solution to my original differential equation is just untranslate this, right? Okay, well, let's do that. Let's finish this off. I'm going to have to erase this work, but this is what I want to untranslate in order to finish this off. Now, of course, in order to do that, the first thing I have to do is what? Partial fraction decomposition. God, I love partial fraction decomposition. I have no idea why, but ever since I took Calculus 2, I think, Calculus BC, took Calculus 2 umpteen years ago. I'm not telling you how long ago. That's been absolutely one of my favorite things. All right, let's go ahead and decompose this. So, what I know that s squared minus s plus 10 over s minus 2 s plus 1 s minus 1 that is equal to a over s minus 2 plus b over s plus 1 plus c over s minus 1. It's going to be a very, very easy decomposition for us. All of these factors are all linear and they're all unique. That's great. It means I can achieve a complete decomposition here by just plugging in example values for s. I'll choose 2, -1, and 1, obviously representing the zeros for the denominator polynomial here. Again, 3 zeros, 2, -1, and 1. So I'll plug in -1, plug in 1. And again, this works because, of course, this equation is true for all possible values of s. And if it works for every possible value of s, it's got to work for these, right? So let's plug in 2 and let's see what happens. You know what? No, I'm going to write it. I'm going to plug those values in, but let me multiply through by the denominator to get the equation we actually want to work with. Okay, so if I multiply through by this denominator, here's what I get. Some of you are probably already ahead of me. Sometimes you just get excited and you just want to move through to the next step. All right, fantastic. All right, so again, plug these things in. So let's plug in 2. And again, when I plug in 2, it's going to kill off these two terms. Why? Because that has s minus 2 and s minus 2. 2 minus 2 is 0. That's 0. That's 0. If I plug in 2, the only thing that survives, left-hand side, I get 2 squared minus 2 plus 10. That's 12. Right-hand side, I get a times 2 plus 1 is 3. 2 minus 1 is 1. That's 3a. And I get a is equal to 4. Same thing's going to happen for plugging in -1 and 1. Let me go ahead and plug in -1. If I plug in -1, again, this term's going to die. This term's going to die. I'm just going to be left with over here. I've got -1 squared minus -1. That's 2 plus 10. That gives me 12 is equal to, the only thing that survives over here is b. I've got b times -1 minus 2 is -3. -1 minus 1 is -2. -3, -2 makes 6. 6b. b is equal to 2. And my last cheater value here, go ahead and plug in 1. Plug it in over here, I get 10. And if I plug in 1 over here, that term's going to die because of the s minus 1. That term's going to die because of the s minus 1. Plug it in over here, I get c times 1 minus 2 is -1. 1 plus 1 is 2. I get -2c. c is equal to -5. Okay, so I now know what I would like to decompose. So let me go ahead and write that down. So I've got y is equal to the inverse Laplace transform of, let me go ahead and write that out. I've got 4 over s minus 2 plus 2 over s plus 1 plus -5 over s minus 1. Okay. And what is this equal to? Well, again, these scalars can be taken out from each of these individual inverse transforms. And then, of course, these are all these are all exponential functions, right? This leads me to, let me write it above. Let me erase this stuff. I'll write it above. We'll go back to black now that we've stopped the decomposition. So we've got y is equal to 4 times the inverse Laplace transform of 1 over s minus 2 plus 2 times the inverse Laplace transform of 1 over s plus 1 minus 5 times the inverse Laplace transform of 1 over s minus 1. These translate very easily. This is 4 e to the 2t plus 2 e to the negative t minus 5 e to the t. That is fantastic, right? And again, and this is one of the powerful things about Laplace transforms, right? It takes something that was maybe involved like a lot of calculus or something like that, and we now have a way to do this that doesn't involve calculus, right? It doesn't involve really very difficult mathematics at all, okay? But you got to develop a lot of machinery in order to make it work for the Laplace transforms, yeah? Now, again, this is not the reason Laplace transforms are actually used so often. That's piecewise functions. We're going to get there, I promise. But that's in 3 more sections. We still have to do first shifting theorem. I'll do a short little lecture on unit step functions, Heaviside functions, and then of course after that we'll do second shifting theorem, which is how we handle piecewise functions. Of course, that's sort of the goal, to be able to handle these things with piecewise functions. Okay. All right, so guys, as normal, homework, it's posted online. Go ahead and get that done as soon as you can. I don't know if you guys are working, when you guys are working the homework. Please try to work the homework before you watch the next video. Yeah? I get the feeling some of you are just kind of like blowing through the videos and like maybe putting the homework off. Don't do that, okay? All right, get your work done. See you guys.